Alright, today's lesson is going to start the next unit on gases. Let's start talking about properties of gases. Okay, you should know some of this stuff from a previous class. We've talked about properties of solids, liquids, and gases actually a little bit in here as well. But you should be aware that a gas basically has no definite shape and no definite volume. What that means is that the gas, it can fill and occupy any size container we take. So no matter how irregularly shaped the container is, the gas will take that particular shape because it just expands to fill up the container. Now, from the last section, what we talked about intermolecular forces at the end. So if we have two particles, if I have a gas particle here and a gas particle here, what we're going to find is that the attraction force that holds these two together is called the intermolecular force, right? We talked about that in the last chapter. It could be London dispersion forces, London dispersion, hydrogen bonding, or dipole-dipole. Well, with the gases that we're going to talk about, all of these are going to be really, really weak, mostly London dispersion forces, but we're going to be able to say that this force here, the intermolecular force, can be ignored. That there's really nothing holding these two gas particles together. That's why they're free to expand and fill up any size container and take any shape that they want. The idea behind a gas is that there's nothing holding them back. They're kind of stuck, free to move in any direction and go anywhere they want. Now, this is not a complete truth because we're negligible. We're maybe saying it can be ignored. The intermolecular force is there because if we were to cool it down, eventually we're going to get it back into a liquid phase and a solid phase, and that's when this intermolecular force is going to come back into play. We're going to talk a bit about that at the end of this unit when we talk about ideal gases versus real gases and what's called the kinetic molecular theory. Alright, so you should know they have low density as well because of the fact that there's a lot of space between these. In reality, if you had this gas in a container, you would actually have gas particles that look something like this. I mean, they'd be very, very far apart. And you can compress them down to very, very small spaces. They have low density, meaning there's not a lot of particles in the volume. So highly compressible, low density, and mixtures, every gas can just mix within itself. Okay, so those are some general properties of gases you should be aware of. All right, now, when we talk about gases, we need to talk about some various types of variables that we're going to see with our gases. We need to talk about pressure, volume, temperature, and how much gas. So when we talk about gases, you're going to see me talking about all of these variables quite a bit. So we're going to see how pressure changes, what effect it has on volume, and what effect it has on temperature, and how much gas you have in the container. We really have already talked about volume. We use milliliters for volume, we use Celsius, and we use Kelvin for temperature, and I've already listed it down here. Obviously, amount is going to be in moles. It tells us how much gas we actually have. Okay, that pretty much answers how much. What we haven't really talked about much is pressure. Okay, there's a number of units that we have for pressure, and this is one of the things that's a little confusing for students in the beginning here, is that there's different units, and it all has to do with the origins of pressure. The one that we're going to use most often is 1 atmosphere, or the atmosphere unit. So ATM stands for atmospheres. Okay, so it stands for atmospheres. So the idea is that there's different ways of measuring pressures with different units. You might have, in our everyday life in the United States, we use pounds per square inch. Well, we're not going to really get into that. We're going to be looking at the metric conversions, and we're going to look at these various ways to convert back and forth. So you may have a gas that's 2.13 atmosphere, and they might ask you, what is that in torr? Okay, so you're going to have to make the conversion from one unit to another. Okay, and I'll talk about where these origins of these units come from a little bit in just a minute. So how would I do this? If I have this pressure, if my pressure is equal to 2.13 atmospheres, and I need to get my pressure into units of torr, I'm just going to use dimensional analysis like I did in previous units, right? So we're going to start using some more math again, so you might want to brush off your math skills. So 1 atmosphere is equal to how many torr? 760. So what I can do is I can do this calculation here, and I can easily convert to my torr. So dimensional analysis that we did before. Okay, so if I multiply this out, I end up getting 1,618.8 torr, which if I use my significant figures, I have 3, so I should round this to 3. So 1620 torr would be my final answer. And nothing startling, pretty simple calculation. I'm not going to sit here and bother with going through all the various combinations. You're given this on the test. You don't have to memorize any of these conversion factors. You just have to know how to convert between the two. We'll look at some practice in class. All right. So let's get into some of the origins. The most common gas that you deal with on a day-to-day basis is your atmosphere. All right, and the atmosphere, you should know, is mostly composed of nitrogen gas. 78% of it's nitrogen. The next most abundant gas is oxygen, which is good for us because we need that to breathe. And we breathe in all of these gases every time we take a breath, but we only use the oxygen. We exhale pretty much all of these back out. Now, one thing you should also realize is that the air it kind of piles up on top of itself. So if you have the ground and you go up higher and higher into the mountains, okay, what tends to happen is you have all this air that's obviously in the air, I guess. All these air particles here. Well, as you get higher up in the atmosphere, the air gets thinner, right? You might have experienced this if you've ever been to Colorado. But if you're down here at this point, you actually have all of this air pushing down on you and kind of, exerting pressure on you all the time. As you go up to the mountain, as you go up to the top, the air pressure is lower because there's less air particles pushing down on you. So as you go higher and higher and higher, you can actually see pressure gets lower. This is what's called an altimeter, is actually used to measure that altitude. And that's how airplanes can figure out how high they are in the atmosphere based on the air pressure that's outside. Okay, so as gravity pulls the air particles down, it makes it more dense and obviously more air particles here. All right, and these patterns change when we have changes in weather. Well, actually, the weather is caused by changes in pressure. So if you have a high pressure region and a low pressure region, it's usually where storms are going to be found. So a lot of times in weather, if you decide to go into weather, are you interested in that? If you watch the Weather Channel, you might see those capital H's and those L's that go by. It's because they're measuring the pressures in the air, the highs and low pressures. All right, so just some interesting stuff about the atmosphere and some stuff about gases. And the last thing I'm going to leave you with is the tool that was used to measure air pressure. This was devised by Evangelista, I normally can say it, Evangelista Torricelli, which is an Italian scientist who came up with this idea of measuring air pressure. The idea is he's measuring those air particles that are pushing down, because remember, you got the air all around here. Well, the air is exerting pressure on the surface of this liquid mercury, and as it does so, it's going to keep the mercury from spilling out. So what you do is you take an inverted tube and you fill it with mercury and you submerge it into a pan of mercury. Well, what should happen is all the mercury should pour out and kind of overflow and spill all over the floor. But that's not what happened, because the air pressure pushes down and it matches the air pressure pushing down inside the tube. And so therefore what he did was he measured this distance, as I kind of covered up, was 760 millimeters of mercury. And that's where that unit comes from. 760 millimeters of mercury was measured to be the air pressure at sea level. Okay, so that's at sea level, and that is our 1.0 atmospheres. Okay, so that's where that unit comes from. Now, people didn't like using millimeters of mercury, of course, because it's kind of a silly unit, so they changed it to the torr, and that's where we get that 1.10 again. So that's why we go from millimeters of mercury to torr, because we're naming it after Torricelli. All right. So that would be how we would measure air pressure. And obviously, the higher up in the atmosphere you go, the lower the air pressure, the lower the column goes. So he was able to find a way. Now, we've got more sophisticated ways of measuring air pressure, but this was the first barometer that was ever devised to measure air pressures, which kind of another little interesting fact there. All right, so that's the introduction to gases. So I'll see you in class, and we'll kind of talk a little bit more about this stuff. And I guess that's pretty much it. So I'll see you later, guys.